Assalamualaikum warahmatullahi wabarakatuh. Now we come to the last part of our chapter 5, which is Sturm-Liouville Problem. Okay, in this section, we will discuss the special types of boundary value problem in which the ordinary differential equation which contains parameter lambda. Okay, the value for lambda should possess non-trivial solutions. Then we call the lambda is eigenvalues, and the corresponding solutions are called eigenfunctions. Okay, this is the regular Sturm-Liouville problem. Okay, for example, we have y double prime plus lambda y equals to 0. Okay, this is the homogeneous second order differential equation. Okay, here the value of a1 and b1 cannot be 0 for both, but it can be 0 for either a1 or b1. Same goes to a2 and b2. Okay, since for the regular Sturm-Liouville problem, normally it is a homogeneous BVP and always possesses trivial solution, which is y equals to 0. So our task is to find the values of lambda which possess non-trivial or non-zero solution. Okay, for example, here we have y double prime plus lambda y equals to 0. This is second order differential equation, homogeneous second order differential equation, since we have equals to 0 here. And y0 equals to 0, and given y0 equals to 0 and y pi equals to 0, meaning here when x equals to 0, y equals to 0, and here when x equals to pi, y equals to 0. Okay, we have since we have three conditions. Okay, first case, lambda equals to 0. Second case, lambda less than 0. And third case, lambda greater than 0. Okay, let's consider case 1 first. For lambda equals to 0. Okay, if lambda equals to 0, our equations will become y double prime plus 0 equals to 0. So y double prime equals to 0. Okay, the auxiliary equation for this is m square equals to 0. So here m1 equals to m2 equals to 0. Okay, that means we have real repeated roots. Okay, remember from our previous chapter 2, the general solution for real and repeated roots is y equals to C1e m1x plus C2x e m2x. Okay, since our m1 and m2 equals to 0, so we have C1e 0 plus C2x e power 0. So we have y equals to C1 plus C2x. Okay, this is the general solution for real and repeated roots. Okay, then we consider the BVP. Okay, when y0 equals to 0, so we substitute x equals to 0 into the solution. So 0 equals to C1 plus C2 times 0. So here will become 0. So our C1 equals to 0. This is for C1. Okay, then the second value, y lambda equals to 0. Okay, so y pi equals to 0. Y pi equals to 0. So we substitute x with pi. So 0 equals to C1 plus C2 pi. Okay, C1 we have 0, so C2 also equals to 0. So both our constants C1 and C2 are 0. So we have trivial solution. So here we don't want the trivial solution. So we proceed with second case. Case number 2. Case 2. For case 2, we have lambda less than 0. Okay, if lambda less than 0, so our differential equations will become y double prime minus lambda y equals to 0. So our auxiliary equation will become m square minus lambda equals to 0. So m equals to plus minus set lambda. So here we have real distinct roots. Real distinct roots. Okay, the general solution for real and distinct root is y equals to C1 e lambda x plus C2e negative set lambda x. Or we can write the solution in another form. Y equals to C1 cos lambda x plus C2 sin lambda x. Okay, then we can apply the boundary value problem. So given y0 equals to 0, so when x equals to 0, y equals to 0, so we substitute x with 0. So y equals to 0, C1 cos okay, sorry, here not like this. Actually, cos set lambda x since set lambda x. Okay, cos lambda x when x equals to 0, so cos 0 plus C2 since 0, so this is equals to 0. Okay, cos 0 is 1, so C1 equals to 0. We have C1 equals to 0. Okay, then we use the second value problem. Y pi equals to 0. Okay, y pi equals to 0, meaning when x equals to pi, y equals to 0. So we substitute x with pi, so 0 equals to C1. Since our C1 is 0, so become here 0 plus C2 since set lambda pi. So from here, C2 also equals to 0. So again, we have trivial solution. Both C1 and C2 is 0, so we don't want this. So we proceed with the third case. Case 3, when lambda greater than 0. Okay, for lambda greater than 0, our differential equation become y double prime plus lambda equals to 0. So our auxiliary equation will become m square plus lambda equals to 0. So from here we will have m equals to 0 plus minus set lambda I, which is complex conjugate form. Okay, so from here, this is 0 is alpha and set lambda is beta. Okay, since we have complex conjugate root, so our general solution will become y equals to e alpha x C1 cos set lambda x plus C2 sin set lambda x. Okay, since here our alpha is 0, so e power 0 is 1. So our solution will become y equals to C1 cos set lambda x plus C2 sin set lambda x. Okay, this is the general solution. Okay, then we apply the value problem, boundary value problem. So y0 equals to 0, meaning when x equals to 0, y equals to 0. So y equals to 0, C1 cos set lambda x we substitute with 0 plus C2 sin set lambda x equals to 0. So sin 0 is 1 cos 0 is 1, sin 0 is 0. So C1 equals to 0. Okay, then we apply the second value problem. Y pi equals to 0. Okay, meaning when x equals to pi, y equals to 0. So here 0, y equals to 0. Okay, C1 we have 0, so 0 plus C2 sine set lambda pi. Okay, we will get C2 equals to 0, but we don't want the trivial solution, so we try to adjust. Okay, so 0 equals to C2 sine lambda pi. Set lambda pi equals to inverse sine 0. Okay, see the curve for sine, the graph for sine. Okay, here 0, pi, 2 pi, 3 pi. Okay, so inverse sine 0 from this curve, from this graph, inverse sine 0 equals to 0, pi, 2 pi, 3 pi, 4 pi, and pi. Okay, so we can write set lambda pi equals to n pi. So set lambda equals to n pi over pi. So we have set lambda equals to n. So lambda equals to n square. This is our eigen value. This is our eigen value. Okay, then we substitute lambda equals to n square into the general solution y. So we have y equals to C2 sine set lambda pi. So y equals to C2 sine sorry, not pi here, actually lambda x here. So sine n x. Okay, this is our eigen function.